When you watch a skyscraper being built, there is a comforting predictability to it.
Oh, absolutely. It's classical physics, right, on a macroscopic
Yeah,
scale.
exactly. I mean, we understand gravity, we understand tension. You see the steel beams go up, the concrete being poured. It's just solid.
Right, the materials behave exactly as we expect them to.
You rivet a steel beam into place, and it stays there. It doesn't suddenly change shape.
That would certainly be a problem for the construction crew.
Yeah, it really would. But imagine trying to build that exact same skyscraper, except your building blocks are microscopic.
And they're constantly vibrating.
Yes. They're vibrating, they're occasionally vanishing entirely, and sometimes they, I don't know, whisper to the blocks next to them so loudly that the entire structure just spontaneously shatters.
It's a complete structural nightmare.
It is, and that structural nightmare is exactly what quantum physicists are facing right now.
It's the bleeding edge of fundamental science.
It really is.
Yeah.
So we are looking at a massive new breakthrough in stabilizing quantum computers today, but also the messy reality of how the current AI boom is disrupting the funding for this kind of fundamental physics.
And of course, how these scientific leaps are actively, physically changing the world you live in.
Right. It is a phenomenal stack of sources we have curated for you today, pulling from ACM Tech News, Quantum Magazine, specifically their physics, biology, and computer science sections, and some really revealing reporting from Science Magazine.
It's a great mix of theory and real-world application today.
Okay, let's unpack this, because we have to start with that vibrating, shattering skyscraper.
Right, the quantum computing dilemma.
Yeah. We've known the theoretical power is there for a while now. I mean, a recent report from Quanta's computer science coverage noted that researchers are actively reducing the time and the number of qubits needed to crack standard online security.
Which is exciting, but also terrifying for cybersecurity.
Oh, totally.
Yeah.
But to execute those code-breaking algorithms, you need stable building blocks. You need what they call high qubit fidelity.
Right. And that brings us to this massive milestone reported in ACM Tech News.
Yes, tell me about this, because this sounds huge.
It is. So scientists from IBM, RWTH Aachen University in Germany, and a startup called Quantum Elements achieved a brand new record for qubit fidelity.
Okay.
They basically maintained this high-fidelity calculation for the longest period ever recorded on a superconducting quantum computer.
Wow.
And crucially, they did this using the 127-qubit IBM systems.
Okay, let me stop you right there. Because 127 qubits sound like a very, very specific number.
Yep.
Why is that scale so important to point out?
Well, it's all about the physical architecture. Superconducting qubits are essentially these tiny, supercooled electronic circuits.
Right.
When you only have a few of them, they are relatively easy to isolate from each other. But when you pack 127 of these physical qubits together on a single chip to do more complex math, their electromagnetic fields start to overlap.
Ah, okay, so they start interfering with each other.
Exactly. It creates a very specific engineering problem that these IBM systems suffer from, known as ZZ crosstalk.
ZZ crosstalk. Okay, so the sources specify that this is generated by the physical proximity of the qubits. What is actually happening to them physically?
It's essentially a phase error. Basically, the quantum state of one qubit physically alters the energy frequency of its neighbor.
Oh.
So if one qubit is in a certain state, it inadvertently shifts the phase of the adjacent qubit, which corrupts the entire calculation.
Oh, I see.
Yeah, it's the physical manifestation of decoherence, the loss of that delicate quantum state.
That makes sense. So imagine ZZ crosstalk is like being in a crowded room where everyone is talking over each other.
That's a great way to picture it.
It's just a mess of overlapping frequencies. Now, typically, how do we handle that? Do we just try to, filter the noise out after the calculation is done?
Traditionally, yes, or you try to design hardware that physically spaces them out more.
But that limits your computing power, right? Because you can't pack as many in.
Exactly. But what this team did was entirely different. They didn't just filter the noise after the fact. They actually suppressed the crosstalk errors before they even happened.
Wait, hold on. If you are suppressing the noise before it happens, aren't you essentially predicting the quantum behavior?
Mm-hmm.
But I thought the whole point of quantum mechanics is that the state is inherently unpredictable until you measure it. Does that break the rules?
See, that is the genius of this approach.
Yeah.
They aren't measuring the quantum state of the information itself. They are characterizing the deterministic interference patterns of the hardware.
Oh, Okay.
Right, because the physical layout of the 127 qubit chip is fixed. It doesn't change. So they can model exactly how these qubits will electromagnetically interact with each other.
Okay, I am tracking with you now.
Once they have that hardware model, they apply very specific counteracting microwave pulses to the qubits.
Oh, wow. So they are essentially piping in an inverse microwave frequency to perfectly cancel out the expected interference right as it happens.
Precisely. And then they coupled that preventative physical measure with existing algorithmic error correction tools.
So it's a two-pronged attack.
Yeah, it created a completely novel hybrid protocol. You were dealing with the physical architectural flaws at the hardware level while simultaneously running software error correction.
So to update my crowded room analogy, this new hybrid protocol isn't just handing you a pair of noise-canceling headphones.
Right.
It's actually predicting who is about to shout in that crowded room and hushing them with a perfectly timed counter sound wave right before they open their mouth.
Yes. It is a brilliant engineering feat. And what's really fascinating here is how this touches on one of the deepest mysteries in physics right now.
How so?
Well, over in Quanta's physics section, Philip Ball recently wrote about this broader concept of decoherence. He suggests that understanding and controlling decoherence might finally bridge the quantum classical divide.
Meaning what exactly? Like bridging the gap between those microscopic vibrating blocks and our macroscopic skyscraper.
Exactly that. For a long time, physicists viewed the quantum world and the classical world as almost two completely different realities with different rules.
Right.
But decoherence is the mechanism that forces a quantum system to basically choose a classical state when it interacts with its environment.
Okay.
So mastering qubit stability, stopping that decoherence in a massive 127 qubit system isn't just a clever engineering trick to crack cryptography faster.
It's bigger than that.
Much bigger. It is the fundamental bridge required to bring quantum mechanics out of the theoretical lab and into applied reality. We are essentially learning how to force the quantum realm to survive in our classical world.
That is just mind-blowing. But getting to that point, making these massive leaps in
Yeah.
quantum mechanics and fundamental physics, it requires immense resources, right?
Oh, absolutely.
You need super cool dilution refrigerators, massive labs, huge teams. And right now, the hot new technology on the block AI isn't just accelerating research. According to Science Magazine, it is actively cannibalizing the budgets of fundamental science.
Yes, and the scale of this resource shift is truly unprecedented. The Department of Energy, the DOE, has launched something called the Genesis mission.
The Genesis mission. Sounds very sci-fi.
It really does. It's a $293 million push into artificial intelligence, led by Dario Gil, who is the DOE's Undersecretary for Science.
And I mean, $293 million does not just materialize out of thin air.
It does not.
To fund the Genesis mission, the DOE's Office of Science is skimming 10% from its traditional research budgets. Budgets that the sources explicitly note are already stretched incredibly thin.
We really have to look at the mechanics of how the DOE functions to understand why this 10% cut hurts so much.
Let's do it.
The Office of Science is basically the nation's premier builder of massive infrastructure. We're talking about particle accelerators, immense X-ray light sources, neutron scattering facilities.
Big stuff.
Right. And historically, they've aimed to spend more on actual research grants for scientists than on simply operating those giant facilities.
Which makes sense. You build the tool so people can use the tool.
Exactly. But Harriet Kung, the acting director, recently explained that operations now consume more of the budget than the research grants do.
Wow. Let's look at the real-world math on that, because the sources break this down. Take nuclear physics. Their total budget is $866 million.
Which sounds like a lot.
It does. But because just turning on the lights and running the cooling pumps at these facilities eats up more than half of that money, the actual cash available for research grants fell by 18% this year. It dropped down to just $196 million. And now they're losing another 10% of that slice to this new AI initiative.
Right.
Researchers are terrified that there will be zero funding left to renew the ordinary grants that are expiring this year.
And honestly, the execution of this Genesis mission has been a bit chaotic. Researchers were given a brutally short window, just 6 weeks after the funding was announced, to put together entirely new AI-centric proposals.
6 weeks! That's insane! There's an example in the sources about Rosie Reed, a nuclear physicist at Lehigh University.
Yes, her situation is a perfect example.
She's trying to teach electrodynamics, advise 30 undergrads, and supervise her grad students. And suddenly she has a month and a half to find partners at a DOE national lab or a private company, survive her university's internal vetting process, and submit a massive grant proposal.
All in 6 weeks. And Nadia Foman at UT Knoxville pointed out another crazy hurdle.
What's that?
The researchers have to figure out how to evaluate their own AI advantage for the proposal.
Which is a particularly frustrating directive, because the DOE admitted in a webinar to like 5,000 scientists that the agency itself doesn't exactly know how to evaluate AI advantage yet.
They are quite literally building the airplane while flying it.
I really have to push back on the logic of this entire system.
Go for it.
Let's say you're a physicist trying to figure out how the universe expands, or what happened right after the Big Bang. Or you're looking at microscopic meteor crystals to find out how the Milky Way was born.
All real topics quantum physics reported on this month, by the way.
Exactly. So you're doing this incredible work, and suddenly you have to force your foundational research into an AI-shaped box just to keep the lights on.
It's a drastic shift.
Isn't that putting the algorithmic cart before the fundamental horse?
Well, it highlights a very deep tension in how we currently value discovery. On one side of the argument, AI is an undeniably powerful tool that might fundamentally change how we perceive data.
Okay, fair.
For instance, Quanta's computer science section reported on this incredibly compelling phenomenon. Distinct, highly advanced AI models seem to be converging on a singular, almost platonic way to encode reality.
Wait, what does that mean, a platonic way to encode reality? How does a computer program do that?
So AI models process information by mapping it into high-dimensional mathematical spaces.
Right.
A vision model maps pixels, while a large language model maps text. What researchers are finding is that as these models get larger and more advanced, the geometric shapes of their data clusters are starting to naturally align.
I'm not sure I follow.
So the spatial representation of a dog in a vision model's mathematical space is geometrically aligning with the spatial representation of the word dog in a language model space.
Oh, well.
They are independently finding a universal mathematical geometry for reality.
That is mind-blowing. So the models are essentially discovering the underlying mathematical blueprint of concepts, regardless of whether it's an image or a word.
Exactly. And that kind of pattern recognition is a tool physicists desperately need to sift through, say, petabytes of collision data from an atom smasher.
Okay, I see the value there.
Dario Gil argues that getting fast, AI-driven results will demonstrate value and secure more funding long-term, which is just a political reality in Washington.
I get the politics, but the structure of these grants is just so rigid. I mean, Challenge 14 from the Genesis funding announcement is titled, Unifying Physics from Quarks to the Cosmos.
Quite a lofty title.
Right. But a university can only lead one proposal per focus area. So if a school has brilliant world-class teams in nuclear physics, particle physics, and cosmology, they have to battle each other internally just to submit one single AI-themed proposal.
And that is the core risk here. By forcing all foundational science into a framework optimized for immediate AI integration, we risk neglecting the pure, unoptimized curiosity that historically leads to the greatest leaps in human knowledge.
We might be narrowing our field of vision just when the data suggests we should be widening it.
Exactly.
It is a frantic scramble for the future. But to be fair to the applied side of this, when fundamental data science and AI do successfully translate into applied science, the physical results we are seeing right now are just extraordinary.
They really are. The translation from theory to physical application is accelerating dramatically. We are seeing a major theme emerge across all these sources: the mastery of scale.
From the microscopic to the massive.
Exactly.
Let's start at the microscopic scale. In medicine, researchers at the universities of Mississippi and Maryland, led by Elam Doe, are using 3D printing to create something called spenlastics.
Spenlastics, they are essentially microscopic carriers filled with cancer-fighting drugs.
Right, but it's how they are deployed that is so interesting to me.
Oh, yeah.
Instead of an IV drip that pumps chemotherapy throughout your entire circulatory system, which obviously has terrible side effects, they're using advanced 3D printing techniques to construct these tiny biodegradable delivery vehicles.
And then they implant them directly.
Exactly. They implant this construct directly at the tumor site. The spenlastics slowly release the medicine exactly where it's needed, destroying the tumor cells locally.
It is localized precision at a cellular level. But of course, to deliver medicine at that microscopic scale, we first have to be able to see the cellular neighborhood we're targeting.
Right, and historically, optical microscopes hit a physical limit based on the wavelength of light.
Which brings us to one of the wildest things in the quantum biology stack this week: expansion microscopy.
I was hoping we'd get to this.
They are completely bypassing the optical limits of the microscope by physically enlarging the cells themselves.
And the mechanism they use to do this is just fascinating. They use a highly absorbent polymer specifically, a key ingredient found in disposable baby diapers.
Okay, you have to explain this. How does diaper polymer magnify a cell?
Right. It sounds crazy. So the researchers infused the biological tissue with the chemical building blocks of this polymer. The polymer physically binds to the proteins inside the cell.
Okay.
Then they add water. The hydrogel network absorbs the water and expands isotropically, meaning it swells equally in all directions.
Fascinating.
It physically pulls the molecules of the cell apart, maintaining their exact relative geometry, but making the entire structure up to 100 times bigger.
That is incredible.
It gives us an unprecedented high-resolution view of microbes using just standard lab microscope.
We are using diaper polymers to physically inflate the microbial world. That is just incredible, and AI is stepping in once we have that view, right?
Yep. Machine learning algorithms are digesting the absolute reams of genetic data we get from these expanded cells to map entirely new neighborhoods in the brain.
They are organizing vast quantities of neurobiological data that a human lifespan simply isn't long enough to sift through.
It's amazing. And that integration of AI isn't just happening in biology. We are seeing it transform consumer tech at the macro scale, too.
Yes, ACM Tech News highlighted a really cool system called Watch Hand, developed by researchers at Cornell and Kest.
Here's where it gets really clever. If you want to track someone's hand movements in 3D, like for virtual reality or smart device control, you usually need cameras or a bulky glove. Watch Hand doesn't use cameras at all. It uses the tiny existing speaker on a standard smartwatch to emit continuous, inaudible sound waves. Sonar, basically.
The acoustic physics here are so elegant. The smartwatch speaker emits these pulses, the sound waves bounce off the contours of your hand and fingers, and the smartwatch's microphone catches the returning echoes.
But the echo data has to be a mess, right?
It is. The real breakthrough is the AI algorithm running in the background. It takes that messy acoustic echo data and maps it to a full 3D skeletal model of your hand in real time.
That is so cool. And we're also seeing this kind of mapping at a citywide scale.
Oh, the 5G drone tracking?
Yes. Researchers at the University of Science and Technology of China used a live 5G advanced base station in Shanghai to track a drone along 25 flight paths.
Without radar.
Exactly. By analyzing the radio signal reflections with machine learning, they tracked the drone with over 96% accuracy. It is vastly cheaper than building dedicated radar systems.
It's a beautiful example of taking existing, ubiquitous infrastructure, a smartwatch speaker, a 5G cell tower, and using algorithmic processing to extract entirely new physical capabilities from it.
So we have 3D printed microscopic tumor medicine, diaper polymer microscopes, AI sonar on our wrists, and 5G drone tracking.
It sounds like an unstoppable wave of progress.
It really does. But there's a massive reality check hiding in these sources.
Yeah, the physical infrastructure bottleneck. We want to run all these advanced AI models to track our hands and map our brains, but that processing requires massive data centers.
And right now, the physical world is pushing back hard.
ACM Tech News reports that there are roughly 12 gigawatts of data center capacity expected to come online in the U.S. this year alone.
Just for context for you listening, 12 gigawatts is roughly the power output of 12 nuclear reactors.
It's massive, but close to half of those planned builds are projected to be delayed or canceled entirely. Only a third are actually under construction.
And the reason isn't a lack of funding or a lack of digital data. It's a shortage of critical electrical components.
Specifically, things like transformers and specialized switchgear, which are largely produced in China.
Think of it this way. It's like we have successfully engineered the world's most advanced brain with these AI models.
Okay.
But that brain requires an incredibly robust circulatory system, transformers, and copper wiring to feed it enough electricity to function. And right now, the circulatory system simply cannot be built fast enough.
That's a perfect analogy. And furthermore, the data that feeds that brain is becoming a geopolitical battleground.
The hack?
Yeah. The sources note that hackers allegedly breached a state-run Chinese supercomputer recently. They stole 10 petabytes of highly sensitive data,
10 petabytes.
including aerospace engineering schematics, military research, and massive bioinformatics databases,
Yeah.
and they are now selling access to it on the dark web for hundreds of thousands of dollars in cryptocurrency.
It is a stark reminder of the physical vulnerability of all of this. If we connect this back to the bigger picture, we see how incredibly interdependent these fields really are.
Definitely. Look at someone like Mate Zaharia, who just won the ACM Prize in computing for his foundational work on distributed data systems and machine learning at scale.
Zaharia's work is essentially the digital scaffolding for all of this, right?
Exactly. He created the software infrastructure that allows us to take a massive volume of data, say, from an expanding universe simulation or a drone's 5G reflections, and distribute that processing across thousands of computers efficiently.
His data infrastructure is what makes the AI boom possible. But Zaharia's elegant digital frameworks and the quantum hybrid protocols silencing crosstalk and the AI models finding a universal geometry for reality, all of it remains completely tethered to the messy physical constraints of global supply chains.
You cannot outcompute a lack of copper wire.
You really can't. The theoretical ceiling is infinite, but the physical floor is dictated by transformers, cooling systems, and the basic realities of physics. Well, we have covered a massive amount of ground today. We started at the absolute microscopic limit, hushing the phase-shifting crosstalk of 127-qubit quantum systems so they don't shatter their own calculations.
We waded through the frantic 6-week scramble for DOE physics funding as AI demands its slice of the fundamental research budget.
And we emerged into an applied world where we were using sonar on smartwatches, physically expanding cells with diaper polymers and 3D printing tumor treatments, all while waiting on delayed electrical transformers to power the data centers making it possible.
It's all connected.
It is. So what does this all mean? Why should you, listening to this right now, care about a squabble over Department of Energy funding protocols or the fidelity of a superconducting qubit in a lab in Germany?
That's a fair question.
You should care because the invisible, highly theoretical battles happening in these labs right now are actively writing the script for the applied medical and consumer technology you will rely on a decade from now. The algorithms and the hardware struggling for funding today are the cancer treatments and the digital tools of tomorrow.
And that leaves us with a critical, lingering question to consider. If artificial intelligence becomes the mandatory, exclusive lens through which all fundamental science is funded and evaluated, what unimaginable discoveries might we miss simply because they couldn't be neatly optimized by a machine learning algorithm?
That's a great point.
Will the next great scientific revolution come from a machine identifying a pattern in the data, or from a human who was allowed to just look at the universe without a 6-week deadline and simply wonder?
Are we building our skyscraper with solid, well-understood steel, or are we hoping the vibrating blocks just happen to hold together? Something to think about. Thanks for joining us on this deep dive, and we'll catch you next time.